Problem 26, another pendulum problem. I'm going to try to make these a little speedier, even though this is a pretty involved one. You always have the option to uh, go back and rewatch something, but I think if you see a bunch of long problems, then you're less likely to watch them all. So I just wasted 20 seconds of this problem saying that. So anyway, go! Okay, that's not what I wanted. So, so pendulum, mass m on the end, length L, 60 degrees to the vertical, 60 degrees, and initial velocity that way. No, velocity, yeah, velocity at the bottom that way. And I'm going to draw a line here for calculation purposes. It doesn't say anything about this in the problem, but we're going to call this h from here to here. And we're going to call this y. Alright, we're also given that m is 2 kilograms, L is 4 meters, and v is 8 meters per second. That's the velocity at the bottom. Part A. Part A, we need to find the speed when the string is 60 degrees. So, actually, this arrow's in the wrong way. V. Yeah, so it goes up that way. So, we need to find the speed when it reaches 60 degrees with the vertical. Well, we'll define zero potential energy at the very bottom, so that's nice. So we'll just do some conservation of energy. We got gravitational potential at 60 degrees plus kinetic energy at 60 degrees is going to equal the gravitational potential at the bottom. It's a B. Plus kinetic energy at the bottom. And so we know that this is mgh, where h is this height here, plus 1/2 m velocity at 60 degrees squared. And that's going to equal 0 because at the bottom we have no potential energy. That's where we defined it to be 0. Plus 1/2 m v bottom squared. Alright, now how big is h? Well, we know that h is L minus y. L is the length of the whole string. Get rid of y, the y part of that, and you get h left over. And we also know that cosine of 60 equals y over L. That's this triangle here. And so y equals L cosine 60. So h equals L minus L cosine 60. And that's going to be 4 minus 4 cosine 60, which is going to equal 2 meters. So that's how big h is. So now this filling in what we know here. This is m. Oh, the m's cancel, and that's nice. So this becomes 9.8 times 2. We just figured out h. It's 2 plus 1/2 velocity at 60 squared equals 1/2 velocity at the bottom is 8. That was given. So solving for v60, velocity at 60 is 4.98 meters per second. That's part A. Part B, we need to find the greatest angle that it will reach, meaning it's how high the maximum height it goes up here in a sense, which is where the kinetic energy is 0. That's nice. So we got, again, conservation of energy. The energy, the total mechanical energy. This, by the way, is mechanical energy at 60. and this is the mechanical energy at the bottom, and they are equal. So now we want the mechanical energy at the max height, and so that's going to equal the mechanical energy at the bottom. So that's just going to be Ug max plus Ke max equals U G bottom plus Ke bottom. And so this is just mgh max plus 0, yay, equals 0, yay, plus 1/2 mv bottom squared, m's cancel. And what's h max? H max is 1/2 vb squared over g. Just solving for h max here, just brought the g over. And h max also equals, using the same logic as we, ow, that hurt, sorry, same logic as we did up here, it's going to equal L minus, let's start over here, L cosine of the max angle, bigger than 60 it should be, and so we're going to set this equal to that, L minus L cosine theta max equals 1/2 VB squared over G. And plugging in numbers, we got 4 minus 4 cosine theta max equals 1/2 8 squared over 9.8. Algebra, solve for theta max equals 79.4 degrees. And as I guessed, it should be larger than 60 because we've gone up higher. Part C is asking if the potential energy of the pendulum earth system is 0 at the lowest point. We've been doing that. What is the total mechanical energy of the system? Total mechanical energy. Well, I talked about that up here. The total mechanical energy is going to equal, well, we got 3 places now we could figure it out. We could do it at the max angle, at 60 degrees, or at the bottom. Let's just do the bottom. They should all agree, by the way, because it's nice. At the bottom, all we got is kinetic energy, and we already know VB. So that's just Ke at the bottom, plus Ug at the bottom, again, which is 0. So that's just going to be 1/2 mass velocity bottom squared, 1/2 times 2 times 8 squared, and that equals 64 joules. Alright, this is a nice problem. You're going to be using stuff like this in other problems, so this geometry and all that, so that's good to know. Our first real super duper conservation of energy problem. We haven't really brought in springs. Well, we did in the past problem, but anyway, yeah.